describes an experimental program designed to determine the potential hazards associated with the storage and handling of liquid hydrogen. This program was carried out by Arthur D. Little Incorporated at their test facility located at Otis Air Force Base, Massachusetts, on Cape Cod. The liquid hydrogen for these tests was stored in a refrigerated transport dewar and transferred to small test dewars. For large-scale tests, transport dewars were used to supply the test material. Is a colorless liquid with a boiling point of minus 423 degrees Fahrenheit or 20 degrees Kelvin. Liquid hydrogen is hazardous because it may form a detonable mixture when vaporized and mixed with air, and it may also react explosively with solid air condensed into the liquid hydrogen. Here, liquid hydrogen is boiling over a bed of sand in a closed container. Removal of the cover allows air to enter. The white cloud is condensed air and water vapor. Solid air, which forms at minus 357 degrees Fahrenheit, collects on the walls of the dewar. Initial tests were made to determine if liquid hydrogen, when accidentally released, as might occur in the event of a storage tank failure, would detonate when ignited. The first tests in this series were undertaken with 1 1/4 gallon quantities. 50 tests of this type were made to determine detonation effects. In these tests, liquid was spilled into a pit. The vaporized gases were then ignited with a spark source. Ignition time delay and spark heights were varied. No detonations were observed. In fact, there was little or no pressure developed by the combustion. The quantity of liquid hydrogen was then scaled up to 32 gallons. Simple bulk-insulated containers proved adequate for holding the liquid hydrogen long enough to run the test. These dewars also facilitated transportation to the test area. Results of these tests were similar to those with a smaller quantity, with no tendency to detonate noted. Radiation measurements indicated a thermal flux level of less than 10% of black body radiation. A period of 30 seconds was required to evaporate the 32 gallons. The encouraging results with small quantities prompted further scale-up to 600-gallon and 5,000-gallon spill tests. The 600-gallon test served to demonstrate the effects of delayed ignition on initial fireball size, while the 5,000-gallon test, which was ignited immediately after spilling, provided useful information on flame size. To better observe the rapid dispersal of hydrogen vapor, this test was photographed at 1/3 normal speed. Wind velocity during the test was 20 miles per hour. Combustion was initiated 8 seconds after rolling the tank over and spilling the contents. The flame in this 5,000-gallon test, although almost invisible, exhibited the same radiation characteristics as in small-scale tests. Here is an infrared film of the previous scene. Analysis of these data provided flame size information, which was applied to establish new quantity distance criteria for liquid hydrogen storage. The maximum flame height was approximately 150 feet. Spill tests with JP4 and gasoline were also carried out to demonstrate the difference in thermal radiation hazard between these fuels and liquid hydrogen. This flame, as well as the gasoline flame, showed a thermal flux density 12 times that of the liquid hydrogen. 7 minutes were required to evaporate the 32 gallons used in this test. Gasoline exhibited the same flame characteristics as JP4, but evaporated in 5 minutes. This typical 32-gallon spill of liquid hydrogen provided a low level of thermal radiation and evaporated in approximately 30 seconds. Spill tests of liquid hydrogen demonstrated that under these test conditions, hydrogen-air mixtures would not detonate. However, detailed information was needed on hydrogen detonation characteristics. This information was obtained by experiments using gaseous hydrogen-air mixtures in 5-foot diameter latex spheres. In this test, photographed at 2,000 frames per second, an explosive initiator was used and a detonation of the hydrogen-air mixture was obtained. Overpressures of 10 pounds per square inch were measured 15 feet from the center of the sphere. However, spark initiation produced only combustion. No overpressure was observed. From the results of these tests and the spill tests, it was concluded that radiation was the primary hazard from large-scale liquid hydrogen spills. To provide conclusive evidence that liquid hydrogen vapor mixed with air would not detonate, spill tests with explosive igniters were carried out. In this test, a 4-gram charge of explosive was used. No measurable pressures were obtained. These films, taken at 1,000 frames per second, showed the initial flash of explosive and the propagation of the flame front through the combustible mixture of hydrogen and air. No detonation wave can be detected. Tests were made to determine the explosive potential of solid air in liquid hydrogen. It was found that these materials would detonate only when the percentage of oxygen in the air was increased to 40% or greater. Initiation of the reaction was obtained with a fusible wire. The explosion occurred at the bottom of the test dewar, propelling a column of liquid hydrogen into the air. Film speed on these two shots was 2,000 frames per second. Liquid hydrogen, when released as the result of a pipeline rupture or spill, forms a combustible mixture which may present a hazard at some distance from the source. Here, a cloud of water vapor and hydrogen gas formed by the release of liquid hydrogen is observed to remain close to the ground at a distance of 600 feet from the point of release under proper atmospheric conditions. Ignition of liquid hydrogen flowing from a break in a transfer line produces a large, totally invisible flame. These infrared pictures of the combustion of liquid hydrogen at the rate of 150 gallons per minute were used to estimate flame sizes for quantity distance calculations. Maximum flame length observed was approximately 100 feet. These tests were designed to investigate the distance which a flame would propagate in a liquid hydrogen cloud formed by a pipeline rupture. The maximum distance the flame front moved from the source was approximately 90 feet, although the cloud of gas and water vapor extended 400 to 500 feet. The results of these and other tests carried out in this program, combined with extensive analytical work, provided a quantitative basis for the establishment of realistic safety criteria in the storage and handling of liquid hydrogen. In general, it was concluded from this program that liquid hydrogen is safer to handle than had been previously considered. Mixed with air under unconfined conditions and ignited by a source other than an explosive, it does not detonate, and radiation effects resulting from liquid hydrogen fires are less than those of more conventional fuels. On the other hand, its low initiation energy requirement and its wide flammability limits make ignition more likely. More care must, therefore, be taken to remove all potential ignition sources from a storage area and to design facilities to withstand the effects of fires resulting from accidental ignition.